The tide pool looks harmless in the late afternoon light. Shallow water trapped between rocks warms quickly, becoming a glassy window into a miniature world of crabs, algae, shells, and small fish drifting between shadows. This is the edge space where people relax their guard. Shoes come off. Hands reach down. Phones come out. The scale of everything shrinks, and with it, the sense of danger. Somewhere in that pocket of water, pressed flat against a rock the color of sand, sits an animal smaller than a golf ball, quiet, compact, almost ornamental. It does not flee. It does not flare its arms or posture like something dangerous. It waits. The blue-ringed octopus survives precisely because it does not look like a threat. Evolution has shaped it to disappear first, to blend into rubble and coral fragments so completely that predators pass within centimeters without registering it as food. Its default mode is stillness. Octopus skin is a living display panel, layered with chromatophores and reflective cells that let it match the surrounding color and texture almost instantly. In calm conditions, its body reads as beige, tan, or mottled gray, another pebble, another scrap of reef. In tide pools, this camouflage fools not just fish and birds, but humans whose brains are tuned to scan for large, fast, obvious dangers. People don't pick up blue-ringed octopuses because they are reckless. They pick them up because nothing about the animal triggers fear. That miscalculation is the foundation of every incident. The octopus is small. Its movements are slow and deliberate. When disturbed, it doesn't bite immediately. It tries to escape, jetting weakly or tucking itself deeper into a crevice. When that fails, when a hand closes around it, when fingers block the exit, when pressure is applied, it reveals the signal it has been carrying all along. Blue rings bloom across its skin in high-contrast electric color, pulsing and spreading like circuitry coming online. This display is not a threat display in the mammalian sense. It is not an attempt to intimidate or chase. It is a warning flag raised at the last possible moment, a biological equivalent of a system alert that appears only when all passive defenses have failed. Those rings are often misunderstood because they appear dramatic and beautiful. To human eyes, they read as decoration or spectacle, something worth photographing rather than retreating from. In reality, the display is metabolically expensive and brief. The octopus cannot hold it indefinitely. It flashes because it must, because it is about to use the only defense it has left. Unlike many venomous animals, the blue-ringed octopus does not inject venom through fangs designed to hunt. Its venom evolved as a defensive override, delivered through a small beak that punctures skin almost imperceptibly. Many victims never feel the bite at all. There is no tearing pain, no dramatic wound, no blood in the water to announce that something has gone wrong. The toxin involved, tetrodotoxin, is not exotic or aggressive in how it works. It does not burn tissue or destroy cells. It does something far more dangerous in survival terms. It interrupts communication. Nerves rely on electrical signals to carry instructions from the brain to muscles. Tetrodotoxin blocks the channels that allow those signals to propagate. The result is not chaos, but silence. Muscles don't spasm. They don't convulse. They simply stop responding. The body becomes a system with power, but no control, consciousness trapped inside a frame that no longer executes commands. This is why the early phase is so deceptive. After a bite, a person may feel only mild tingling around the lips or fingers, a numbness that resembles dental anesthesia or cold exposure. Breathing feels normal at first. Heart rate remains steady. There is no immediate collapse that forces urgency. In tide pool scenarios, this delay is lethal. Tourists walk back to the beach. Parents continue supervising children. Someone laughs it off as a jellyfish sting or a scratch. The venom is already circulating, binding where it needs to bind, quietly closing doors inside the nervous system. As paralysis spreads, it does so symmetrically and without warning. Fingers lose coordination. Legs feel heavy, then unresponsive. Speech slurs, not because the brain is failing, but because the muscles that shape words are dropping offline. Breathing becomes shallow as the diaphragm weakens. Victims are often fully conscious throughout this process. They can see, they can hear, they can understand exactly what is happening while being unable to signal it effectively. This is the true horror of tetrodotoxin exposure. Not pain, but isolation inside your own body as vital functions queue up and fail. In ecological terms, this toxin is a borrowed weapon. The octopus does not manufacture tetrodotoxin itself. It accumulates it through symbiotic bacteria associated with its tissues and diet. This relationship allows a small, soft-bodied animal with no shell and limited escape speed to occupy exposed environments like shallow reefs and tide pools. Predators that sample it, fish, eels, even sharks, either learn quickly or do not survive the lesson. Over time, this creates a quiet exclusion zone around the species. Blue-ringed octopuses do not need to dominate territory or hunt aggressively. Their presence alone reshapes behavior around them, a chemical boundary enforced through evolutionary memory. Humans, however, sit outside that memory. There is no inherited avoidance of small octopuses glowing blue. In fact, curiosity drives the opposite response. Children are especially vulnerable because the animal fits perfectly into the category of safe discovery. Small hands, shallow water, bright colors, and a moment of adult distraction is all it takes. In many documented cases, the octopus is returned to the water after being handled, the danger already transferred. By the time symptoms escalate, the source is gone, and critical information is missing. Medical response depends heavily on recognizing what happened quickly, because survival hinges on supportive care, keeping the person breathing until the toxin is metabolized and nerve function returns. This is where delay becomes the real killer. Tetrodotoxin does not destroy the nervous system permanently at typical exposure levels. With ventilation and monitoring, many victims can survive until the toxin clears. Without intervention, respiratory paralysis can be fatal, even though the heart and brain remain intact. The margin between those outcomes is measured in minutes and recognition. The absence of drama at the start, the lack of bleeding, pain, or visible trauma creates a false sense of safety that costs time the body does not have. From the octopus's perspective, none of this is malicious. It is a last-ditch survival mechanism deployed when camouflage fails and escape is impossible. After biting, the animal often releases immediately and attempts to flee, expending precious energy to get away from the threat it perceives. In natural encounters with predators, this works. In human encounters, the mismatch in scale and understanding turns a defensive adaptation into a lethal trap. The octopus does not chase. It does not seek contact. Every incident begins with someone closing the distance first. Seen this way, the blue-ringed octopus is not an assassin hiding in plain sight. It is a stress test for human perception. It exposes how badly we read danger when it does not conform to size, speed, or aggression. In the tide pool ecosystem, it plays a quiet regulatory role, deterring oversampling by predators and maintaining balance through chemical deterrence rather than force. In human spaces, it reveals a deeper problem. Our instinct to touch, collect, photograph, and share overrides the simple rule that in unfamiliar ecosystems, beauty is often a warning written in a language we haven't learned to read. When the rings appear, the message is already late. They are not there to scare you away. They are there because every other option is gone. In that moment, the animal has reached the end of its escalation ladder. What happens next is no longer about behavior or choice, but about chemistry and time. The tide pool closes again as water drains back to the sea, leaving behind nothing but wet rock and footprints. The octopus disappears into a crevice, its skin dull once more, carrying no memory of the encounter. The human story, if it continues at all, moves inland, into ambulances, ventilators, and the thin window where awareness finally catches up to reality. This is the danger of things that look like toys but function like switches. They don't announce themselves as threats. They wait for you to decide they are safe. In the rainforests of northern Australia and New Guinea, there is a moment that traps people into making the wrong decision. It happens when something large steps out of the green and does not flinch. No crouch, no alarm call, no retreat. Just a towering bird with a glossy black body, electric blue neck, and a helmet-like casque that looks more ceremonial than dangerous. The cassowary does not read as prey. It also does not read as predator. To a human brain trained on mammals, it registers as an anomaly, exotic, ancient, strangely calm. That misread is the opening move in almost every serious incident. Cassowaries do not fear people in the way deer or kangaroos do. They evolved in dense forest where the biggest risks come from close-range encounters, not distant pursuit. Running blindly through undergrowth is inefficient and dangerous. Standing ground, reading posture, and responding explosively when thresholds are crossed is the strategy that works. When a cassowary does not move away from you, it is not being friendly. It is assessing. And because humans are upright, slow to turn, and visually noisy, we often fail that assessment without realizing we're being tested at all. Approach behavior is the real danger amplifier. People walk closer because the bird doesn't flee. They stop because they want a photo. They linger because the animal looks composed. Some feed it, thinking food equals control. Others bring dogs, assuming size dominance applies across species. Each of these actions collapses distance in a space where distance is safety. Cassowaries are not aggressive by default, but they are uncompromising about personal space, especially when chicks, food sources, or escape routes are involved. The weapon that ends these misunderstandings is not the beak. It is the foot. Cassowaries carry a long, dagger-like claw on the inner toe of each foot, stiffened and sharpened by evolution to act as a cutting instrument. This claw is not decorative. It is anchored to powerful leg muscles capable of explosive extension. When a cassowary kicks, it does not swing wildly. It drives forward and upward, aiming for the abdomen, groin, or chest, areas where soft tissue and major blood vessels are exposed. The motion is fast, precise, and brutal in its efficiency. Mechanically, the kick is devastating because of leverage and mass. Cassowaries can exceed 50 kilograms, and their legs are built for sudden acceleration over short distances. They do not need a running start. From a standing position, they can launch forward with enough force to open deep lacerations or puncture organs. The claw does not need to sever an artery cleanly to be lethal. A single penetrating wound, combined with shock and blood loss, is enough to end the encounter permanently. This is not speculation. Documented fatalities exist, and near-fatal injuries are more common than people realize. The real risk pattern is consistent and repeatable. Dogs are the #1 trigger. A dog approaches barking, lunging or circling, exactly the behavior that mimics a predator probing for weakness. The cassowary responds as evolution dictates: neutralize the threat quickly. Owners often insert themselves between dog and bird, collapsing distance even further. Feeding is another reliable catalyst. A cassowary that has learned to associate humans with food loses its natural spacing rules. When food is withheld or contested, the bird escalates. Cornering is the third. Trails, fences, vehicles, and human bodies can block escape routes, turning assessment into action. Understanding what to do when charged requires abandoning mammalian instincts. Running triggers pursuit. Turning your back removes your ability to read posture and respond. High-pitched noise and frantic movement amplify the bird's perception of chaos. The correct response is counterintuitive, but grounded in physics and behavior. Back away slowly while facing the animal. Increase perceived size by keeping arms up and using objects as barriers, not weapons. Trees, backpacks, bikes, even a jacket held wide can break the bird's line and give it a reference point other than your torso. The goal is not dominance. The goal is de-escalation through space. Cassowaries are not relentless attackers. They deliver force to resolve a problem, then disengage. If distance opens and the bird's path clears, escalation often stops. This is why obstacles matter. A simple trunk between you and the bird can redirect a charge into a sidestep. A slope or uneven ground can disrupt the launch mechanics of the kick. These are not tricks. They are ways of respecting how the animal moves and what it needs to disengage. To understand why cassowaries behave this way, you have to see their ecological role. As major fruit eaters, they are keystone dispersers. Seeds of large rainforest trees pass through their digestive systems intact and are deposited far from the parent plant, often in nutrient-rich packages that boost germination. In some forests, entire plant lineages depend on cassowaries for distribution. This makes the bird both ancient and essential, an ecosystem engineer wrapped in feathers and muscle. Their sensory world is tuned to close quarters. Dense foliage limits visibility. Sound travels unpredictably. Threats appear suddenly. In this environment, hesitation is punished. Cassowaries evolved to resolve ambiguity fast. Humans interpret this decisiveness as aggression because we expect warning displays, bluff charges, or vocalizations. Cassowaries do not waste energy on those signals. Their warning is posture: head low, body angled, attention fixed. Miss that, and the next message is kinetic. The irony is that cassowaries are often most dangerous when they appear relaxed. A bird calmly feeding, standing still, or walking slowly does not look like a threat. That is precisely when people approach. The moment safety feels assumed is the moment the margin disappears. When a cassowary actually feels threatened, the window for corrective action is already closing. This is not a monster narrative. Cassowaries do not hunt humans. They do not patrol territory seeking conflict. Incidents are situational, not habitual. But the cost of misreading those situations is extreme because the animal's defensive solution is decisive. Evolution did not give cassowaries a warning kick. It gave them a problem-ending kick. Seen clearly, the cassowary is a stress test for human arrogance in wild spaces. It looks like a curiosity until it reminds you that it is a large, fast, heavily armed animal optimized for close-range dominance. The forest does not care that it photographs well. The bird does not care that people underestimate it. The physics of muscle, claw, and momentum remain the same whether you feel safe or not. The final lesson is not about fear. It is about timing. The most dangerous moments with cassowaries are not when they charge out of nowhere. They are the quiet moments when distance closes without consequence, until it does. The first thing most people notice about a sea snake is how unthreatening it feels in the water. Its body moves with a smooth, ribbon-like ease, uncoiling through the reef with none of the abrupt tension people associate with land snakes. The head is small. The eyes are dark and calm. There is no rattle, no hood, no aggressive display. In clear water, the animal often appears curious rather than hostile, weaving between fins or drifting alongside a diver for a few seconds before slipping away. This is the moment when humans make their most dangerous mistake, assuming that a calm interaction equals a safe one. Sea snake bites are rarely dramatic. When they occur, they are often barely noticed. The teeth are short, designed to hold slippery fish rather than tear flesh, and the bite is usually defensive, triggered by pressure, restraint, or entanglement rather than attack. Fishermen pulling nets, surfers tumbling in shallow breaks, divers reaching into crevices at night, all share one thing in common: contact without awareness. When a sea snake bites, it does not chew. It does not latch on. It delivers a quick, shallow puncture and releases. Many victims later describe it as a scratch, a pinprick, or nothing at all. That lack of pain is the trap. Sea snake venom is not built to announce itself. It is not optimized for immediate agony or visible tissue destruction. It is optimized for speed and efficiency inside the bloodstream of fish. Once delivered, it targets muscle cells at a molecular level, disrupting the membranes that keep those cells intact. The process is slow enough to go unnoticed at first, but relentless once it begins. Muscle fibers start to break down, releasing their contents into the blood. This is not paralysis in the dramatic sense. It is internal collapse, one microscopic failure at a time. Because the bite doesn't hurt, people keep going. A fisherman finishes hauling the net. A surfer paddles back out. A diver completes the dive and climbs onto the boat. The ocean, meanwhile, keeps the body moving, masking early weakness. Salt water supports limbs that would feel heavy on land. Adrenaline smooths over subtle changes. By the time the person notices something is wrong, the venom has already done significant work. The progression is insidious. It begins with vague muscle soreness, often mistaken for exertion or dehydration. Arms feel tired. Legs feel sluggish. Grip strength fades. Cramping follows, not sharp spasms, but deep, spreading tightness that doesn't resolve with stretching. Urine darkens as muscle breakdown products flood the kidneys. Breathing becomes effortful as the muscles that drive the chest wall weaken. None of this arrives with a single clear warning. It unfolds like a system quietly losing pressure. What makes this especially dangerous is timing. Sea snake venom acts over hours, not minutes. This delay encourages underestimation. People go home. They sleep. They wait. Meanwhile, muscle damage continues, and the kidneys, tasked with filtering the byproducts, begin to fail. By the time medical help is sought, the problem is no longer just venom in the blood. It is organ stress layered on top of toxin exposure, a cascade that becomes harder to reverse the longer it runs. From an ecological standpoint, this venom design makes perfect sense. Sea snakes hunt fish that must be immobilized quickly in open water. A fast-acting myotoxin prevents escape without requiring the snake to hold on or risk injury. Pain signaling is irrelevant in this context. Fish don't learn avoidance from pain. They either escape or they don't. Evolution strips the venom down to what works, not what feels dramatic. Humans encounter sea snakes most often at boundaries, surf zones, reef edges, fishing grounds, places where animal behavior intersects with human routines. Nets are a recurring problem. Sea snakes are drawn to fish already trapped and struggling, and in the chaos of hauling gear, hands reach blindly into coils of mesh where a snake may be pinned or compressed. In that moment, the snake does exactly what it evolved to do. It bites to create space, not to kill. The venom dose delivered in these encounters is often significant because the bite occurs under sustained pressure, giving venom time to flow. Night dives add another layer of risk. Sea snakes hunt actively after dark, following chemical cues and movement rather than sight. Divers moving slowly with lights become large, warm objects in an environment where contrast is low. Reaching into holes or under ledges without visual confirmation increases the chance of direct contact. Again, the bite itself may not register. Gloves, wetsuits, and water all dull sensation. The clock starts anyway. One of the most counterintuitive aspects of sea snake envenomation is that calm behavior after a bite does not indicate safety. In fact, the absence of immediate symptoms is one of the most reliable indicators that something dangerous may be unfolding. Unlike venoms that cause rapid swelling or necrosis, sea snake venom leaves no obvious local injury. There may be no redness, no bleeding, no swelling to mark the site. The body looks intact, while its muscles are dissolving from the inside. This is why experienced coastal communities treat any suspected sea snake bite as a medical emergency, regardless of how the person feels. Antivenom exists, but its effectiveness depends on timing. Supportive care, hydration, monitoring kidney function, managing respiratory weakness is critical. Waiting for pain to justify concern is a mistake rooted in land-based thinking, where danger is loud and fast. In the ocean, danger is often quiet and patient. Sea snakes themselves are not aggressive animals. Many species, including yellow-bellied sea snake, spend much of their lives drifting in open water, rarely encountering humans at all. Others patrol reefs with methodical precision, conserving energy and avoiding unnecessary conflict. They are air-breathing reptiles that have adapted fully to marine life, with flattened tails for propulsion, valves that close their nostrils underwater, and even the ability to absorb some oxygen through their skin. Their world is one of efficiency and constraint, not confrontation. The tragedy of sea snake bites lies in mismatch. Human skin is thick compared to fish scales, so bites are shallow. Human pain thresholds are tuned to immediate injury, not delayed biochemical failure. Human activity patterns, finishing tasks, getting back to shore, waiting it out, play directly into the venom's strengths. The snake leaves. The story continues. Seen clearly, the lesson is not that sea snakes are stealthy killers, but that the body can be compromised long before it signals distress. The bite is painless because pain would serve no purpose. The venom is quiet because quiet works. In the ocean, not everything dangerous announces itself. Sometimes the most lethal phase of an encounter begins only after you think it's over. By the time weakness sets in, the animal is long gone, gliding through the reef or drifting on a current, unaffected by the chain reaction it triggered. The human, meanwhile, learns too late that survival in marine environments depends less on what you feel in the moment and more on what you respect before the symptoms arrive. In the shallows of a tropical beach, danger does not arrive with motion. It does not break the surface or cast a shadow. It does not signal intent through posture, sound, or speed. It is already there, suspended in water so clear it feels empty. Sunlight penetrates to the sand, flattening contrast, erasing depth cues, turning the ocean into a bright, misleading plane that reads as safe to the human eye. This is where the box jellyfish operates best, not as a hunter that chases, but as a collision hazard disguised as nothing at all. The box jellyfish is not built to be seen. Its bell is nearly transparent, a cube of tissue refracting light instead of blocking it. In calm conditions, even trained observers struggle to spot one unless the sun hits it at the right angle. In shallow water, where waves are small and water clarity is high, the jellyfish visually dissolves into the environment. This invisibility is not incidental. It is ecological strategy. The jellyfish drifts where fish fry, prawns, and small schooling species pass through, relying on chance contact rather than pursuit. For humans wading or swimming, the same rules apply. You don't approach it. You don't provoke it. You simply intersect its space, and that is enough. Unlike animals that rely on a single bite or sting, the box jellyfish delivers harm through repetition. Its tentacles trail behind it like fine threads, often extending several meters, each lined with millions of microscopic stinging cells called nematocysts. These are not passive barbs. Each nematocyst is a pressure-sensitive injector, primed to fire the instant it brushes against skin. Contact does not need to be forceful. A light graze is enough to trigger mass discharge. Where a snake delivers venom through one strike, the box jellyfish delivers it through thousands of simultaneous punctures, each injecting toxin directly into the bloodstream. This is why the pain is so extreme and so immediate. The venom attacks nerve endings and skin cells at once, creating a sensation often described as burning, crushing, and electric simultaneously. But focusing on pain alone misses the real threat. Pain is only the first system to register what has happened. Beneath that sensory overload, the venom is already affecting the cardiovascular system. It interferes with heart rhythm, blood pressure regulation, and cellular ion balance. In severe stings, especially from species like Chironex fleckeri, the body can enter shock within minutes. Shock is not dramatic. It does not look like thrashing or screaming once it takes hold. Blood pressure drops. Blood flow to the brain becomes unstable. Muscles weaken. Coordination collapses. In open water, this cascade is deadly, not because the venom stops the heart outright, but because it compromises the body's ability to stay afloat and breathe. Many box jellyfish fatalities are not caused by venom-induced cardiac arrest alone, but by drowning that follows rapid incapacitation. The ocean does not wait for your nervous system to catch up. This is why box jellyfish stings are so often described as sudden disappearances rather than prolonged struggles. A swimmer feels an explosion of pain, panics, inhales water, loses motor control, and slips under in seconds. From shore, it looks like a routine swim that simply ends. The jellyfish drifts on, unaffected, its tentacles retracted and redeployed as if nothing occurred. The evolutionary logic behind this venom is not cruelty, but efficiency. Jellyfish lack a centralized brain. They do not decide to sting. Their entire survival strategy is built around automatic response. Anything that brushes the tentacles is treated as potential prey. Fish that contact the tentacles are immobilized almost instantly, their muscles locking or failing, allowing the jellyfish to reel them in toward its mouth. Against small prey, this system is brutally effective. Against large animals like humans, it is disproportionately destructive, not because the venom evolved to kill us, but because it evolved to act fast, and fast is unforgiving. This automatic nature of the sting also explains why improper first aid can make things catastrophically worse. Nematocysts do not all fire at once. Many remain unfired on the skin after initial contact, waiting for the wrong stimulus. Fresh water, for example, causes osmotic changes that trigger additional discharge. Rinsing a sting with drinking water or ice does not soothe it. It activates more injectors. Rubbing the area, scraping with sand, or using towels can do the same. Each mechanical or chemical mistake turns a localized injury into a broader venom delivery system. Vinegar stations exist on tropical beaches for a reason. Acetic acid neutralizes unfired nematocysts, preventing them from firing further. It does not remove venom already injected, and it does not erase pain, but it stops the injury from escalating. This distinction matters. Many myths around jellyfish stings persist because people confuse relief with prevention. Vinegar is not about comfort. It is about containment. Understanding when and where box jellyfish appear is another layer of survival literacy that humans often ignore. Stinger season is not arbitrary. It aligns with water temperature, breeding cycles, and prey availability. In northern Australia and parts of Southeast Asia, box jellyfish populations increase during warmer months when shallow coastal waters become nurseries for fish larvae. These same conditions draw swimmers, creating an overlap that repeats every year with predictable regularity. Nets are deployed not because they guarantee safety, but because they reduce probability. They are barriers against drift, not shields against venom already in the water. Even then, nets are imperfect. Box jellyfish can slip through gaps, and detached tentacles can drift independently, still capable of stinging. This is why vigilance matters more than infrastructure. Vinegar stations, warning signs, and patrols exist to compensate for the animal's invisibility, not to eliminate it. The system assumes encounters will happen. It is designed to respond quickly when they do. One of the most counterintuitive survival rules associated with box jellyfish is the instruction to keep moving, specifically, to run once you are out of the water. The reason is physiological. Venom spreads faster when circulation is sluggish and uneven, as it is during panic or collapse. Getting the heart pumping in a controlled way can help distribute venom more evenly, reducing localized overload that can trigger sudden cardiac events. This is not a guarantee of safety, but it can buy time, and time is the only currency that matters after a severe sting. From an ecological standpoint, the box jellyfish is not an aberration. It is part of an ancient lineage that predates most modern predators. Its simplicity is its strength. No bones to break. no organs to puncture, no behavior to misinterpret. It floats, senses, fires, and feeds. In a warming ocean, its range is expanding, not contracting. Clearer coastal waters, reduced predators, and changing currents are creating conditions where encounters with humans are becoming more frequent, not less. What makes the box jellyfish uniquely dangerous is not just its venom, but the way it exploits human assumptions. Clear water feels safe. Shallow beaches feel controlled. Pain feels like the worst outcome. Every one of these instincts is wrong in this context. The box jellyfish proves that the ocean does not need to look hostile to be lethal. It only needs to be indifferent. There is no malice in this animal. It does not hunt swimmers. It does not defend territory. It does not pursue. It drifts, doing exactly what evolution has tuned it to do for hundreds of millions of years. The harm happens at the interface, where a transparent predator overlaps with a species that relies too heavily on vision and too little on understanding systems it cannot see. When people describe box jellyfish as monsters, they are projecting frustration at their own vulnerability. The truth is colder and more instructive. This animal is a reminder that in marine environments, invisibility can be more dangerous than teeth, and that the ceiling of pain is not the point where survival ends. It is the point where everything else begins to fail. In shallow tropical water, danger does not always move toward you. Sometimes it waits beneath you, compressed into the geometry of the sea floor, shaped like the environment itself. The stonefish exists at the exact intersection of human confidence and biological indifference. It does not chase, threaten, or announce itself. It becomes the reef. It becomes the sand. It becomes the rock shelf where people place their weight without thinking. And in that single moment of contact, one careless step, one shift of balance, it delivers one of the most extreme defensive responses in the animal kingdom. Stonefish are masters of visual erasure. Their bodies are not merely camouflaged in color, but sculpted to resemble dead coral, algae-covered rock, or sediment-caked rubble. Their skin is irregular, lumpy and textured, colonized by algae and microorganisms that further blur the boundary between animal and substrate. On a reef, they disappear into complexity. On sandy flats, they partially bury themselves, leaving only the suggestion of shape. On rock shelves, they settle into cracks and depressions where shadows do the rest. Predators scanning for outlines, symmetry, or motion fail to register them as prey. Humans, scanning for anything that looks alive, fail even harder. This invisibility is not passive. The stonefish chooses where to vanish. It positions itself in high-traffic zones for reef fish, near ambush corridors where currents deliver food. It does not need to move much, because food comes to it. Small fish drift too close, are engulfed by a sudden expansion of the mouth, and disappear in milliseconds. For the stonefish, stillness is not vulnerability. It is dominance through patience. For humans, that same stillness is a trap. The danger begins with weight. Stonefish are not venomous because they want to be. They are venomous because they must survive being stepped on by animals far larger than themselves. Their dorsal spines, thick, rigid and sharply pointed, are arranged like a pressure-sensitive minefield along the back. Each spine is connected to venom glands, sealed until force is applied. There is no active strike, no muscular thrust. The delivery system is purely mechanical. When something presses down, the spines are driven into flesh, and venom is injected automatically. The harder the pressure, the deeper the penetration, the more venom is delivered. This is why stonefish envenomation is so severe. A human foot stepping down does not apply gentle force. It commits body weight, momentum, and reflexive balance correction all at once. The instinct to push harder when pain is felt, to regain stability, only worsens the injury. More pressure means more spines engage. More venom enters the tissue. The animal does not escalate. It simply responds exactly to the force applied, converting weight into chemical defense. The pain that follows is not metaphorical. It is not discomfort or sharpness or burning in isolation. It is a system-wide alarm triggered at the highest possible level. Stonefish venom is a complex mixture of proteins that attack nerve endings, disrupt cell membranes, and interfere with pain regulation itself. Signals fire continuously, without modulation. Victims often describe the sensation as explosive, crushing, and radiating. Pain that does not stay localized but climbs the limb, invading joints and muscles far from the original wound. The nervous system is flooded, overwhelmed, unable to down-regulate the signal. This is where panic becomes a secondary threat. Pain of this intensity hijacks attention completely. Rational thought collapses. Breathing becomes erratic. Muscles spasm or lock. In shallow water, this combination is deadly. People fall, submerge, inhale water, or thrash uncontrollably. The stonefish does not need to kill directly. The environment finishes the job. Many serious outcomes are not due to venom toxicity alone, but to drowning that follows sudden incapacitation. From an evolutionary perspective, this makes perfect sense. The stonefish's venom is not designed to kill predators outright. It is designed to create immediate disengagement. Any predator that mouths or steps on a stonefish experiences an overwhelming negative stimulus and learns, if it survives, to avoid that shape forever. This is why stonefish have few natural enemies. The cost of a mistake is too high. Evolution favors predators that remember pain. Humans, again, fall outside this system. We do not learn through generational memory in the same way. Every tourist is a first-time participant. The reef resets the lesson daily. What makes stonefish venom particularly notorious is not just its intensity, but its biochemical fragility. Unlike some venoms that remain stable across a wide range of conditions, stonefish venom proteins are heat-sensitive. This is not an accident. In the animal's natural context, venom only needs to function long enough to deter a predator. It does not need long-term stability. For humans, this quirk becomes a narrow window of relief. Hot water immersion is not a folk remedy. It is chemistry. Proteins rely on precise three-dimensional structures to function. Heat disrupts those structures, denaturing the proteins and rendering them less effective. When the affected limb is immersed in hot but not scalding water, the heat begins to break down the venom locally. Pain relief can be dramatic, not because the injury is healed, but because the chemical signal driving the pain is being dismantled. This does not neutralize all venom, and it does not reverse tissue damage. It does not make medical care optional. What it does is interrupt the feedback loop that turns envenomation into collapse. By reducing pain intensity, it allows breathing to stabilize, movement to become possible, and extraction from the water to occur safely. In survival terms, it buys clarity. And clarity is what prevents a bad injury from becoming a fatal one. Stonefish incidents cluster in predictable places: shallow reefs, sandy lagoons, rocky shelves near shore. They spike during low tide, when people wade rather than swim, placing feet where eyes cannot easily see. They increase in areas where reef degradation leaves more rubble and broken coral, exactly the textures stonefish mimic best. Human impact creates better hiding spots. The animal adapts without changing anything about itself. Ecologically, the stonefish plays a quiet role. As an ambush predator, it helps regulate populations of small reef fish, contributing to balance in crowded systems. Its presence influences how other animals move and feed, creating invisible boundaries of caution. In healthy reefs, these dynamics are stable. In human-dominated spaces, they become hazards. The stonefish does not migrate. It does not patrol territory. It does not pursue novelty. It waits. Its entire survival strategy is built around being mistaken for something else. This makes it uniquely dangerous to humans, not because it is aggressive, but because it occupies the exact blind spot created by our assumptions. We expect danger to move, to signal, to reveal itself. The stonefish proves that sometimes the deadliest animal is the one that does nothing at all. Seen clearly, the lesson is not about fear, but about posture. Where you step matters. How you distribute weight matters. Shuffling feet instead of stepping, using protective footwear, respecting environments where visibility is limited. These are not precautions born of paranoia. They are adaptations, the same kind every successful species develops when entering a new niche. Humans enter reefs as amateurs. The reef does not adjust for us. The stonefish remains where it is after an incident, often unharmed, sinking back into stillness once the pressure lifts. Its spines retract. Its venom glands reset. The environment closes over the event, leaving no trace except a memory carried away by the injured. In this way, the stonefish embodies a broader truth about natural systems. The most extreme consequences often arise not from confrontation, but from contact. Not from pursuit, but from overlap. You do not need to see the stonefish for it to affect you. You only need to forget that the ground beneath you is alive. In the Australian bush, danger does not always scale with body size. Sometimes it comes packaged in something barely longer than a fingernail, moving with mechanical certainty across soil, leaf litter, and lawn edges that people step over without a thought. The bull ant does not hide. It does not rely on camouflage or chemical invisibility. It announces itself through posture, motion, and presence. Large eyes track movement. Long legs elevate the body above the ground. Mandibles remain partially open, ready. This is not an animal designed to kill you. It is an animal designed to stop you immediately. Bull ants are pain specialists. Their venom is not optimized to shut down organs or trigger delayed collapse. It is optimized for one purpose: instant behavioral override. When a bull ant stings, the message is not, "You are dying." The message is, "Whatever you are doing must end now." From an evolutionary perspective, this is far more efficient. Killing a large animal is unnecessary. Stopping it, forcing retreat, dropping tools, breaking focus, is enough to protect the colony. This is why bull ants are often described as carrying a pain weapon rather than a lethal one. Their sting ranks among the most intense of any insect, rivaling species far more infamous for venom potency. The pain is sharp, deep, and persistent, often described as drilling, tearing, or burning, with a rhythmic quality that does not fade quickly. Yet, in most cases, it does not cause systemic failure. There is no widespread tissue destruction, no delayed organ shutdown. What it causes is immediate incapacitation at the level of attention and motor control. The human nervous system treats this kind of pain as an emergency interrupt. Fine motor skills vanish. Grip strength collapses. People drop whatever they are holding, not because they choose to, but because the signal overwhelms voluntary control. Shovels fall. Tent poles are released. Children freeze or scream. The sting does not need to escalate beyond this point, because the threat has already been neutralized. The bull ant has achieved its goal. This design makes sense only when you understand how bull ants live. They are not solitary foragers passing quietly through the landscape. They are territorial, infrastructure-focused insects that invest heavily in trails, nest entrances, and defended zones. Their colonies may be smaller than those of some ant species, but they are aggressively protected. Individual workers act less like expendable units and more like sentries, responding to disturbance with speed and coordination. Swarm logic does not require a swarm in the cinematic sense. It requires rules. Bull ants rely heavily on vibration and movement cues. Footsteps near a nest transmit through soil. Tools striking the ground send shockwaves through root systems and packed earth. Lawnmowers, tent stakes, and digging hands all register as intrusions. Once the signal crosses a threshold, nearby workers converge, not to attack indiscriminately, but to remove the source of vibration. Stings are delivered quickly and often repeatedly if the stimulus continues. This is why bull ant encounters escalate so fast in human settings. Yard work creates vibration. Camping compresses soil near nests. Children running or stomping trigger defensive responses long before anyone realizes an ant colony is present. The ants are not roaming. They are responding to a disturbance inside a defended perimeter. To them, the human is not a giant animal passing through. It is a localized environmental disaster that needs to stop. The sting itself is a finely tuned tool. Bull ant venom contains peptides that target pain receptors directly, triggering intense nociceptive signaling without requiring large volumes of venom. This efficiency allows even a single sting to be overwhelming. Unlike venoms that rely on cumulative dose, bull ant venom delivers maximum effect instantly. The result is not confusion or dizziness, but clarity of threat. Every nerve involved in detecting injury lights up at once. Importantly, this pain does not scale linearly. A second sting does not feel like twice the pain of the first. It compounds the experience, saturating the nervous system further and prolonging recovery. This is why people stung multiple times often describe an inability to think clearly for extended periods. The body remains locked in a defensive state, flooded with stress hormones, long after the ants have disengaged. From the ant's perspective, this is ideal. The threat retreats. The nest remains intact. No further energy is expended. Bull ants do not pursue fleeing intruders far from the nest. Once vibration and pressure subside, the defensive response winds down. The ants return to patrol mode, mandibles still ready, but no longer escalating. This behavior highlights an important distinction between danger and lethality. Bull ants are not killers by default. Fatal outcomes are rare and usually involve allergic reactions rather than venom toxicity. Yet their sting can disable a person in ways that create secondary risks. A fall from a ladder, a dropped power tool, a child running blindly into traffic or water. In this way, the bull ant's impact extends beyond the venom itself. It creates situations where human environments amplify the consequences of sudden incapacitation. Ecologically, bull ants occupy a role that goes beyond pain delivery. They are predators, scavengers, and ecosystem engineers. They control insect populations, recycle organic matter, and aerate soil through nesting activity. Their large eyes, unusual among ants, allow them to hunt visually, targeting prey with precision. This reliance on sight explains their sensitivity to movement and vibration. They are tuned to detect changes in their immediate environment and respond decisively. Species such as Myrmecia gulosa exemplify this strategy. Large, bold, and visually oriented, they patrol with intent, not randomness. Encounters with humans are not accidents so much as overlaps between two very different uses of the same space. To a bull ant, a lawn is not a recreational area. It is defended territory layered with invisible boundaries. The evolutionary logic behind pain as a weapon becomes clearer when viewed through this lens. Killing a large intruder would be wasteful and risky. Pain, however, is cheap and effective. It creates immediate compliance. It teaches avoidance without requiring repeated exposure. Over time, predators that can learn remember these encounters. Humans, again, are slow learners. Each generation rediscovers the lesson independently. The most dangerous misunderstanding about bull ants is the assumption that because they are not deadly, they are not serious. This framing misses the point. Evolution does not optimize for death counts. It optimizes for outcomes. The bull ant's sting consistently produces the outcome it needs: interruption, retreat, space. In many cases, the pain outlasts the encounter by hours, reinforcing the lesson long after the ants have disappeared from view. Children are particularly vulnerable because they lack the context to interpret warning signs. Bull ants do not always sting immediately. They may rear up, open mandibles, and hold position, a visual threat display that reads as curiosity to an untrained eye. Stepping closer, poking, or lingering triggers the final escalation. By the time pain hits, the child's reaction may be chaotic, drawing more attention from nearby ants responding to movement and vibration. In campsites and yards, prevention is less about eliminating ants and more about awareness. Recognizing nest entrances, avoiding repeated ground disturbance in one area, teaching children to pause rather than stomp when stung. These adaptations mirror the behavioral shifts predators make in bull ant territory. They are not acts of fear. They are acts of coexistence. Seen clearly, the bull ant is not a villain and not a joke. It is a living demonstration of how pain functions as an evolutionary brake pedal. It does not destroy. It interrupts. It does not hunt humans. It forces them to stop behaving like they own the ground beneath their feet. In a landscape shaped by fire, drought, and competition, bull ants have survived by making themselves impossible to ignore at the exact moment it matters. Their sting is not a threat of death. It is a demand for distance, enforced through one of the most effective deterrents biology has ever produced.